Thank you, everyone, for joining us on Ventilation Matters. This is a great topic, and I appreciate Andre Schibler spending the time with us to educate us in this area. The topic is distribution of ventilation during mechanical ventilation, and it's one of my favorite topics. I'm sure it's a lot of people's. So, Andres, thank you, and we'll turn it over to you.
Okay. So the topic is ventilation distribution during mechanical ventilation. It's been a hobby of mine to follow that topic, but just for a refreshing as a first go, I just want to show that vets are now advertising using high flow during anesthesia in dogs, and they're advertising now on their web pages as well that they offer high flow during any anesthetic to their little dogs. I just was crossing some papers even that in the vet medical journals that they're using and investigating it. Just thought as an enlightenment that we're teaching the dogs now as well how to use high flow. Okay, now to the topic. There's two ways to look at ventilation distribution. We can do look at anatomical or imaging modality. I'm just scrapping this topic at the surface, but I think bedside, we need to have an understanding of the function of ventilation distribution and how we can measure it. And it's quite sobering that we haven't really made a lot of progress in the sense that the ventilators and the technology to measure functional ventilation distribution would be actually there, but no one picks it up, integrates it into a ventilator, despite from a technical aspect, computing aspect, it would be easily implemented, but no one has actually done it. We lost with the infrared sensor that measured sulfur hexafluoride during the ventilation. We lost that technology about 20 years ago. Siemens had one, and they just didn't produce it anymore, didn't think it is important, and didn't pursue it any further. And so I'm still hoping that a ventilation company will jump on and recognize this is actually a very useful technology. And I'll talk in detail how that can operate. I had the pleasure to meet Manuel Paiva and Silvia Verbank on several occasions. They, the two of them, they have really changed and implemented the way we look at ventilation distribution and how we can measure it. And this slide shows what we know from, if you open West's lung physiology, we know that the upper part or the non-dependent part of the lung is basically distended, and the dependent lower or gravity dependent part is where more of the so-called mechanical change are occurring in volume change. If you can appreciate the graph on the left side is the volume change that occurs in the upper, which is the upper line, and in the lower lung is the lower line. And you can just appreciate that the steepness of, or the slope of these two graphs, they are different. So there's more volume change happening in the dependent lung than in the upper lung. So the aeration is better in the upper lung. That's why we have TB mostly located up in the upper parts of the lung, because they like to have a higher oxygen tension. By the way, that's why people sent TB patients in the 1910, 1920 to high altitude, because they want to lower the oxygen tension and thought that they can, reduce the bacterial load by going in high altitude. So that's as well already reflected in lung physiology in the 20s, that people assumed or knew that this may actually help. So bedside lung imaging techniques. We certainly have imaging techniques available. Our blunt chest X-ray, and that's what we use. We look at the chest X-ray and say, oh, these lungs need to be better inflated, or the base of the lung is collapsed. We have very sophisticated new technology with CT scanning and single photon emission CTs. I'll show some pictures there. I mean, they're creating fantastic images of where the ventilation is distributed. You can almost pinpoint down to certain segments and identify them. But it is not helping bedside because you're going to take a patient into a scanner, do the scan, you know, at that particular time, you know what it is, but how it's going to impact on your ventilation management needs to be shown. We simply don't use it, and it's not practical. Similar as well, we've done some work using hyperpolarized helium. Fantastic technology, has made a huge progress over the last 10 years. So the hyperpolarized helium is basically a waste product from nuclear waste that's been used. So having access to hyperpolarized helium is difficult, but can be used for research purpose as well now for clinical purpose. And the details that you get with the MR is absolutely mind-blowing, because you have a perfusion and ventilation distribution images available. But again, you need to move a patient into MR, and it's cumbersome. It's taken quite a while to get these images. Not that easy. And then, of course, we talked about electrical impedance tomography, which I'm gonna talk a little bit about it, but I would like to really focus on the functional measurement. So we know that when we use EIT and put a patient, or here a healthy subject, in left lateral or right lateral, we see huge changes in ventilation distribution as it occurs in change of lateral or prone or supine position, etc. Again, remember the best distribution. EIT measures where volume change is occurring within the lung. So if we are in right lateral position, so the right lung is the dependent lung, air is mostly moved within that region. If you put then the patient in left lateral position, you get the opposite distribution. So EIT is a fantastic tool to investigate the efficiency of ventilation as it occurs when you do a position change, or when you change your PEEP or your peak pressures, etc. So it's a fantastic bedside modality, but it doesn't tell you anything around the zones that you don't see. So that's on the opposite side, because there's no volume change happening, but this lung is not dead or is not functional. It is just not moving as much air as the dependent lung, for instance. So that's the limitation. EIT can only measure bulk flow or volume change. It can't give you an assessment on how good basically the alveolar space is operating. So that's certainly a limitation of EIT. We can sort of approach with EIT a little bit the question of do we do ventilate in the sense of tidal recruitment? So are we opening and closing lung regions, or are we over-inflating lung regions? By using the EIT, and we can calculate a regional index, it's called the filling index. You can see the line, the darker line is the so-called filling index, measured in a sheep lying on the right side, so the right lung is dependent. And then that's the darker line is the filling of the lung when the lung is healthy. So you can see that when the filling index is above 1, there's slight tidal recruitment occurring. And if the filling in this index is less than 1, there's so-called hyperinflation occurring. So the lung is open, but needs to add a little bit more of lung volume, and we call that hyperinflation. You can see that in a healthy lung in lateral position, the dependent lung is filling and so-called tidal recruitment. The non-dependent upper lung is experiencing tidal hyperinflation. And then we created a smoke inhalation injury, which is more directed to the dependent lung than the non-dependent lung. And you can see after the injury, there's a lot of tidal recruitment happening because that right lung is injured, and every breath is recruiting, closing, recruiting, closing. So we can observe that quite nicely by using this filling index, which is obtained out of an EIT image and is a parameter that can be displayed basically breath by breath and being calculated. Again, as usual, this hasn't made it yet into clinical practice to help us guiding our ventilation strategies. The Drager EIT equipment has actually the capacity to extract that filling index. So it's within the Drager research software, you can have access to it, but the commercial software or the stock standard software doesn't display it. Reason is probably because it's too hard to understand what it means, as usual, and it's hard to translate that into the daily practice of clinicians. Now here, just to demonstrate what more sophisticated CT scanning can do. So in the upper 3 pictures is the ventilation distribution, and in the lower 3 images is the perfusion distribution. Just visually, you can appreciate that if you have ventilation occurring near the residual volume or FRC, that the upper parts have a different color than the dependent lung, whereas in TLC, you can see it's more homogeneous, so the lung is completely expanded everywhere, so that's a healthy lung. So you can really use this technology to identify the regions that are denser and obviously have less volume in comparison to lung tissue. Whereas in the lower 3 images, you can see that the perfusion doesn't necessarily follow a similar pattern. So the diffusion is less gravity dependent. You can see that from a residual volume to total lung capacity, the distribution of perfusion doesn't change that much. So these technologies, they're fantastic. They can really give a lot of information, and you can repeat, for instance, these images in all different regions of the lung and can identify the ventilation perfusion relationships. Gives a lot of information diagnostically, but as I said, we can't use it bedside. Now, that leads us to how should we approach optimal ventilation? So I'm leading here first with a few slides how optimal ventilation should be titrated in theory and how this can be measured with electrical impedance tomography bedside. So if you look at this scenario here, that you have a PEEP of 5 on the left-hand side, and you have one compartment that's collapsed. Then you apply pressure support of 8. The left compartment will hyperinflate and experience plus 13, whereas the right compartment, the second compartment, doesn't experience anything because can't open with a pressure of 8. It's not going to happen. Then if you go into increase of PEEP to 10 and repeat the same, the PEEP of 10 has now open up the compartment, and we have the pressure now delivered into this compartment. We have opened up this lung, and we get a better ventilation occurring there. Whereas the so-called healthy compartment experience as well from 10 to 18, but it's not as huge overdistension that has occurred in the first scenario. Then if you increase the PEEP to 14, these are theoretical considerations. You can see you have the recruitment with possible overdistension of both compartments that are occurring. And if we then reduce the pressure support but maintain the PEEP of 14 in this scenario, we can see that potentially both compartments are starting to be happy without having to experience either tidal recruitment or going from a telectasis to open up. So both compartments probably stay open and do not experience overinflation. And you can appreciate now that the bulk gas flow that occurs during these different scenarios are such as that bulk flow is mostly occurring into the lung that experience a tidal recruitment. So volume change is mostly happening in these areas that are injured. And with not enough PEEP, we further on injure this compartment by closing, opening, closing, opening. And that was what Lachman, about 30 years, said, open the lung and keep the lung open. So you don't have this cycling, injuring scenario occurring. Now, if we look very carefully here in a healthy lung, using EIT. So the zone is, one is the upper zone and zone 4. So let's just concentrate on these two zones only. So that's the dependent and the non-dependent lung, the upper lung. You can see during spontaneously breathing and assisted, we have the airway pressure in the upper panel and then the flow that occurs. That's what's happening at the airway opening. And interestingly, if you measure the so-called volume change, EIT measures, as I said, only volume change, you can see that the timing of volume change in zone 1 and zone 4 are at the beginning of the breath, almost in opposite direction. Which means that when a breath is directed into the lung by spontaneously assist breathing, the lower part of the lung will experience volume change, where we have almost Pendelluft happening when this is occurring. Now, this is a spontaneous breathing patient who uses the diaphragm. And the diaphragm obviously has a dome shape. It's not symmetrical distributed across the lung. And you can see that these posterior parts, and that's where most of the displacement of the diaphragm is occurring. So the change in distance of the diaphragm is occurring most in the posterior part. And that shows here in the EIT which part of the lung is filling first. Whereas if you look at the purely pressure controlled, where the ventilator does the work and the patient doesn't do anything, you can see that the volume change in the posterior part, if you look at these two arrows, the black arrows, the volume change that occurs in the posterior or in the so-called dependent lung is much smaller compared to spontaneous breathing. And that's within the same subject, same region. So you can see that spontaneous breathing does affect the dependent lung hugely differently than when you are in pure pressure-controlled ventilation. So we have imaging technology available that can differentiate between spontaneous breathing and its effect on ventilation distribution compared to pressure-controlled ventilation. Now, I'm leading back here to the four scenarios that we had before: optimized PEEP and spontaneous breathing, optimized PEEP and no spontaneous breathing, so fully pressure-controlled breathing. Now you can see again, I indicated here with the arrow the zone 1 and the zone 2. You can see that during this spontaneous breathing, we have again a similar behavior of the ventilation distribution towards the dependent lung. That means the volume uptake in the dependent lung is going first and then followed by zone 1 later on. During pressure-controlled ventilation, during optimized PEEP and no spontaneous breathing, so during pressure-controlled ventilation, you can see when you have optimized the PEEP, the volume change is very similar as during spontaneous breathing and optimized PEEP. And you can see how adjusting the PEEP and finding the right PEEP, you can achieve with pure pressure-controlled ventilation a similar volume distribution effect as you would like to have during spontaneous breathing. So that means you almost overcome the negative effect that we've seen in the previous slide by pressure-controlled ventilation purely by adjusting the PEEP. Does that make sense? Okay. And if we do the opposite and say, okay, we lower our PEEP, so we lose that benefit of adjusting the optimized PEEP, you can see, just focus on zone 4, again on the volume change between Z and D, which means spontaneous breathing C, and D is pressure-controlled ventilation. You can see we lose immediately that effect of the optimal PEEP by the volume not being distributed in a similar way to the dependent lung. This scenario that we're talking through is just to demonstrate if you carefully analyze the EIT data within these different zones, you can achieve quite a good understanding of how you adjust, for instance, here the optimal PEEP to achieve a more homogeneous ventilation distribution during mechanical ventilation. That's just a summary of it that shows when you have optimized PEEP plus spontaneous breathing or optimized PEEP without spontaneous breathing, that the blue-green looks more homogeneous, and as soon as you lower your PEEP, you lose this homogeneous distribution. And the imaging technology is helping clinically to adjust your PEEP level to the right level. This has been quite a nice piece of work done by a group with Brian Kavanagh previously in Toronto. I'm skipping this slide here and going to the next. So what does that mean for the ventilation? That yes, we have tools available bedside that can look at ventilation distribution or maldistribution, but we only can assess volume change. We can't assess the so-called silent zones of the lung, so the zones that are aerated but may not contribute to the gas exchange or not well enough. So that leads us to how do we understand ventilation distribution? And this is going to be a little bit technical. There's two, let's say, philosophies in looking at how the lung is structured. Functionally, it probably doesn't matter so much, but there's the trumpet model that's coming from Weibel and from Paiva over the time, that basically the airway diameter is opening up towards the acinar space. And then there is the other philosophy that the lung is more orientated in a fractal pattern, that fractal geometry is determining which parts of the lung are better ventilated or less well ventilated. I'm not going into details there, but we need to be quite aware that all the assumptions or all the modeling that we're doing thereafter are based on assumptions how the lung is actually anatomically structured. So the easier one for the simple mind like me is the Weibel model. Just as a side remark, Weibel was one of my professors for lung anatomy in Bern. So his branching model of the lung is quite famous. And what happens is that if we're going down to the generation 14, 15, 16, 18, that's where the lung is experiencing bulk flow or volume change. And there's hardly any volume change occurring after the 18th generation. That's the silent space of the lung. And as med students, you know that if you put the stethoscope onto the lung, you can't hear the alveolar space because there's no dynamic happening in the alveolar space. There's no flow happening. We only can hear what's happening within the airways that are conducting airflow. So volume change in the lung is happening in the airways or in the terminal airways. And so that's where our tidal volume is going, and not into the alveolar space. Now, that's true, of course, now for the healthy lung. As soon as we have collapsed alveolar space that opens and closes during each breath, there will be airflow in the periphery or volume change in the periphery. But the alveolar space is not made for volume change. The alveolar space is made to stay open. That's why we have surfactant. So the interesting part of it is, where does convection occur? Where does convection transit into diffusion? I keep asking my med student, how long does it take if you have a marked oxygen molecule entering your nose till you can measure and see this oxygen molecule at the tip of your finger? And I keep asking them, how long does it take for that molecule to end up at your fingertip? Most answer are maybe 5 seconds, 3 seconds, 10 seconds. The average molecule takes 2 minutes to get there, because the diffusion process within the lung is utterly slow, and it's a huge distance to cover by just diffusion, just by the Brownschen molecular movement. Then the clever students say, but if I give someone who is hypoxic oxygen, the SATs are coming up within 10 seconds. So you're wrong. No, I'm not wrong. I've been talking about a spontaneous breathing person that inhales 21% oxygen. In the lung, we have 21% oxygen. But as soon as we change to 100% oxygen inhaled, the diffusion process within the acinar space is accelerated hugely, because there's a huge gradient in partial pressure, because we change from a 21% to 100%, or a PaO2 of 120 to 650. So there's a huge gradient all of a sudden created that accelerates it. That's why we see the SATs coming up within 10 seconds or 20 seconds. But if we don't change the driving force for the diffusion speed, it takes utterly long for a simple oxygen molecule going from the nose to the fingertip. So does that make sense? So the diffusion characteristics within the acinar space is very important to understand. And interestingly as well, that the lung has matured, or is over the generations of mammals and animals and up to humans. A rat, for instance, they start having acinar space after the 4th, 5th, 6th generation. And newborn babies do have as well, when they're premature, have a different branch. They're still maturing in their branching, but they have a much earlier occurrence of acinous space, of diffusion-dependent space. And that's probably the reason why high-frequency oscillation operates quite well in premature infants or newborns or in little ones, because that distance for diffusion to occur is just located on a very small distance. And high-frequency oscillation is probably accelerating the diffusion processes within the lung. And that's why it's not surprising that adults are not benefiting as much from high-frequency oscillation compared to neonates. And if someone is game enough to look at ventilation distribution in an elephant, I would be very sure that high-frequency oscillation, as we do, is probably not working at all. So you see that the lung geometry and the diffusion-dependent processes are sort of interlinked. Depending on your geometry or anatomy, you benefit more from diffusion-dependent processes, whereas probably adults do not benefit from high-frequency oscillation as much. So that's just a little summary of what I've been just talking, that infants have a different location of that transition between convection to diffusion. So that molecule comes in and moves in with bulk flow, and all of a sudden that flow stops because there's no flow happening anymore, and the molecule now needs to keep moving with Brownian molecular movement, and it will take quite a long time to get to the alveolar space or to the alveolar capillary membrane. Adults have a more distal convection diffusion front compared to infants. So that's just purely related to the anatomy. Terminology around it is in the ventilation distribution physiology that we talk about convection and diffusion. And there's a lot of modeling where and how far down is convection going. This is just to show that more or less the so-called distal air ways, so the bronchioli, they are changing in volume. And then as soon as it gets into the alveolar space, we have a complete diffusion-dependent process in the healthy lung. But in the atelectasis lung, we have cycling, opening, and closing. So that so-called convection diffusion front is really pushed down into the alveolar space, but with unhealthy movement of both, unhealthy movement because alveoli are not made to cycling, opening, and closing, and that's where the lung injury occurs. So how can we now measure this ventilation distribution that's in relation to diffusion processes? Because if we can measure what impacts on convection and what impacts on diffusion and can separate the two. So if we have tools in our tool belt that can say, okay, I've got a bronchial tree that's not very well constructed or is sick, then I have convection maldistribution. Or do I have acinar space that is cycling, opening, or closing? Then convection is happening in there. Or do I have acinar space that just is not participating in the gas exchange? So diffusion-dependent processes. So if I have a tool that can separate convection-dependent ventilation maldistribution or diffusion-dependent maldistribution. So can we separate the two apart? Because they are two important factors in improving ventilation distribution. So how inert gas washout is happening is the following. So what we do is we have the subject breathing first just regularly room air or whatever air is needed. And then we add a tracer gas, either during the wash-in period or the wash-out period. So let's use sulfur hexafluoride. So what we do, we let the subject inhale 5% sulfur hexafluoride over 2, 4, 5 minutes, till we know that the lung is filled with 5% of sulfur hexafluoride. Sulfur hexafluoride is an inert gas, will be not absorbed or hardly not absorbed. It will just stay within the lung. And we know the lung is now filled with nitrogen, oxygen, and 5% sulfur hexafluoride. And then we stop the supply of the inspired SF6, and the lung start to get rid of the SF6 breath by breath, and that's a washout. Okay, so we start looking at washing out that sulfur hexafluoride over several breaths. So if we look at one single washout, so this is a nitrogen washout, doesn't matter if it's different, it looks exactly the same if you use sulfur hexafluoride, and we do one big breath. So we say, okay, you inhale your last sulfur hexafluoride inhalation to your maximum you can, and the next expiratory phase, we measure the exhaled concentration of the sulfur hexafluoride and ask the subject to empty the lung as much as possible. You're all familiar with that graph. It's the CO2 that looks similar. Any other gas that gets exhaled and can be measured simultaneously. We see that phase 1 and 2 are determining the dead space. Then phase 3 is the contribution of the gas coming out of the acinar space. And the phase 4, still a lot of discussion around there. What it really is, it's probably of the very, very slow compartments contributing at the end of a single exhalation. Now, that's how we could measure this slope of this curve is telling us how homogeneous the acinar space, or the diffusion, is delivering the sulfur hexafluoride into the conducting airways. Okay, so the flatter the curve is, the more homogeneous all these acinar spaces are emptying out into the conducting airways. The steeper this curve, the more inhomogeneous the contribution of diffusion is during a single exhalation. Okay, does that make sense? So we could use a single exhalation of a tracer gas and assess how bad the ventilation maldistribution is due to diffusion problems. Again, we can't use that in ICU during mechanical ventilation. It's not a test that's easily being done. So that's more in the physiology lab. Now, what we can do, however, is the following. We can now have a patient's lung filled with 5% of sulfur hexafluoride. Here again, it's a nitrogen curve, but it's exactly the same if you use another gas like sulfur hexafluoride. And you switch the supply off, so the lung is full of 5% sulfur hexafluoride, or here nitrogen, and you just keep measuring the concentration that's exhaled breath by breath. And if you look at breath number 1, you see how flat the slope 3 is. And then you look at breath number 20, how the slope is much steeper. Okay? That means the first breath takes the sulfur hexafluoride of the best acini that are contributing, the healthy ones. Breath number 20 is lagging behind, and then finally the unhealthy parts of the lung, or the so-called lung that suffer most from ventilation maldistribution, starts to show up. That's why we have a steeper slope on breath number 20 compared to breath number 1. Now, this is not only driven by acinar contribution or diffusion contribution, it is as well affected by convection maldistribution, because we may have parts of the lung where the convective exchange is very slow and not very good. Let's say parts of the lungs are bronchoconstricted, and in breath number 1, the good parts are exhaling of the lung that are in good convection shape as well. So what's happening if we start plotting, and that's where it gets a little bit complicated, but I'll hope can make it very simple. We're looking at breath number 1 and breath number 20, the slope. Okay, now we start plotting this, and then we have to do a little bit normalization around these slopes. We need to normalize it for the indeed exhaled volume at this particular breath. You can see in a healthy lung, that's an example during a bronchoconstriction. So the dark, the filled circles is at resting state before bronchoprovocation. You can see there are these slopes plotted from breath number 1 to breath number 20. Yes, they sort of gradually increase a little bit, but not much change. It's more or less a flat pattern. Then we strict the patient with bronchoprovocation, and all of a sudden you can see that the slopes are starting to increase from breath to breath to breath. These are the open circles. So we have quite a fantastic mean to demonstrate when the ventilation convection-dependent maldistribution is changing. You can see that the slope, or if you put a slope through these dots, you can see that you can identify the convection-dependent maldistribution quite neatly from the normal. And you can see the arrow down where it says diffusion-dependent. You see that the first breath that the patient has exhaled has exactly the same slope, or roughly the same slope. Just the first black dot and the first open circle in that graph. You see they're almost matching. Because the first breath, the slope is dependent on acinar or on diffusion dependent contribution to the slope, where the ones that are following, they're more influenced by convection dependent. Okay, you can see this patient before and after bronchoprovocation. Makes sense. A bronchoprovocation does only affect convection dependent distribution, doesn't affect acinar. So a bronchoprovocation or an asthmatic doesn't have an acinar problem, they have an airway problem. That's why the circle dot and the open dot are matching. Okay, now let's go in COPD type land in principle. You can, that's just again a repeat of what I said before. This is as well, again, if you look at the triangles, that's before, and the circles are the so-called sick lung. So that's a comparison between normal lung and convection maldistribution affected lungs. You can see that the triangle and the circles are matching. That means the diffusion dependent differences are not occurring, where the convection dependent are quite dominant. Now let's look at COPD. So we know COPD is a diffusion problem, or can have a diffusion and convection problem. So emphysema without airway issues, or emphysema in combination with airway issues. So on the right graph, I just put the asthma, what we discussed on the left side, so you can compare. And now look on to the right side, there are two different scenarios of COPD-1 and COPD-2. So COPD-1 is with lesser airway issues, and COPD-2 is a combination of airway and acinar space issues. And at the bottom, you see what a normal lung should look like, where this arrow sits at the bottom near acinar. You can see that's roughly what a normal acinar contribution should look like, so diffusion dependent. You can see that the COPD-1 value sits well above norm, but the following breath afterwards do not show much convection distribution problems, whereas the triangle or COPD number 2 has a combination of both, has a combination of a huge offset. You can see this patient's first breath has a value around 0.7 compared to 0.2 or 0.1 of the COPD without airway issues. And you can see as well the slope there afterwards goes up. So there's the combination of convection dependent and diffusion dependent ventilation maldistribution. And so you can see we can use this technology to separate convection dependent and diffusion dependent processes in one test. And it can be done during mechanical ventilation because we can fill the lung with a tracer gas, switch the tracer gas off, and measure the exhaled concentration. We can measure CO2, we can measure sulfur hexafluoride, we can measure nitrogen, methylene. There's a lot of tracer gas that can be used. So that helps us if we want to look at ventilation distribution. I just show you a very, very, very simple approach that we have done using similar technology. If you look at the sulfur hexafluoride exhalation in a child without PEEP on the left side. Just look at the curve. It's a logarithmic scale on the left side. And then we added PEEP on the right side. And you can see how the so-called end tidal SF6 concentration is more linear in this logarithmic scale. And the so-called improvement of ventilation distribution from a non-linear to a linear exhalation of tracer gas is already helping us to say, okay, we have more homogeneous ventilation distribution. And that's a simple graph that can be used bedside. You just need a cylinder of sulfur hexafluoride and an infrared analyzer that's similar to our CO2 analyzer in near the endotracheal tube, and you can measure that. So we measured that change of ventilation improvement using sulfur hexafluoride. We didn't use an infrared sensor, we used the ultrasonic flow sensor, which is measuring the molecular mass of the gas exhaled. But you can see this is quite an easy way to go and look at how you can improve ventilation distribution. Just to rejuggle our memory just towards the end, what I've described is nothing new. We all know that because we know that the CO2 signal tells us a lot about ventilation maldistribution due to diffusion dependent processes. We know that the slope, if it gets steeper, then we have more maldistribution of the acinar contribution to the ventilation distribution. Just to finish it off, a very nice experiment that a Swedish group has done. They increased the PEEP from 0 to 10. Obviously, the patient was anesthetized, and at 0, they had lots of atelectasis. And when they increase the PEEP to 10, they start opening up alveolar space. And you can see that the end tidal CO2 the exhaled CO2 is first dropping because we need to have a redistribution of lung volume, drops, but then starts, so that's the uppermost graph, and then gradually we start exhaling CO2. So that very simple experiment shows that if we change from 0 to 10 centimeter of water and we carefully measure the exhaled volume of CO2, we get quite a good impression how the ventilation distribution has been changed in a matter of a second. So it's quite a nice experiment, and it's even an experiment that you can do bedside if you have volumetric CO2 measurements, because you see that volume of CO2 exhaled will first drop and then gradually increase, but that demonstrates that you have recruited alveolar space because you get more CO2 contribution there afterwards. So to summarize, where does that lead us with that technology? So I'm a strong believer that we should have inert gas washout integrated with the ventilator. I mean, technology is there. You need a cylinder of sulfur hexafluoride lasts for about 100 patients. You hardly use anything. It's cheap, doesn't cost anything. It's harmless, but can be added into the ventilation circuit, can be easily measured with an infrared sensor that you can attach to the endotracheal tube. And we can measure conductive airway-dependent ventilation maldistribution, as I've shown with these COPD graphs, for instance. So we can start playing with the ventilator and playing with the RC element of the lung, because that's the convection dependent part of the ventilation distribution. And then because we can assess as well the diffusion dependent, that's the first slope of the first breath, if there's an offset, if that changes from before or after increasing PEEP or peak pressures, we have means in our hand where we can say, yes, this PEEP change had a huge impact on the ventilation maldistribution or improvement over time in ventilation maldistribution. So the inert gas washout is, in my view, the only technology currently available that can separate volume change or airway related ventilation maldistribution, and at the same time can give us information about the diffusion processes or the diffusion dependent maldistribution within the lung. So unfortunately, even after 20 years of looking into the topic, we still don't have the means available. I've been talking to ventilator companies, but I think whenever I start talking about it, it gets lost in the translation because it's utterly complicated. But once you get the gist of it, it's actually quite simple. If you understand these graphs and you can analyze these graphs and you can see the differences. So I thank you for taking the patience to look at, talk through that quite hardcore physiology. But let's hope in the next 20 years we'll see some improvements there. And I know, Steve, you're probably hugely in favor to support this.
I am indeed. I am indeed. Well, thank you, Andres. This has been a great topic and a great talk. So I have a question about the role that diffusion has with gas exchange. I know Rademacher's article talked about the influences or the differences in the mechanisms of oxygenation versus CO2 removal. And I wonder, what does focusing on this diffusion have in relationship to gas exchange, to O2 delivery versus CO2 removal?
I mean, let's separate it or separate the two. Oxygen or oxygenation is a diffusion problem. Or if you have an oxygenation problem, you have more or less a diffusion problem. That's a little bit crude, but it's a function of how much alveolar space do we have available and how high the so-called diffusion gradient within the acinar space is. And then obviously alveolar capillary membrane diffusion is another problem there, but that's not ventilation related. It is diffusion within the tissue.
Right.
So oxygenation is a diffusion problem, and CO2 removal is more a convection-dependent issue. However, as the last experiment by looking at the CO2 removal from 0 to 10 ppb in the Swedish experiment, there is, of course, as well a CO2 diffusion problem. If you have airways, they collapse and open. Because when it's collapsed and you immediately open the airspace with the inhalation breath, then the CO2 needs to find its way out via a diffusion process first. And since the inhaled gas has 0 CO2 and the alveolar space has a much higher CO2 concentration, the diffusion is much faster for the CO2 because there's a gradient. With the oxygen, it is not. So CO2 benefits from a huge gradient in the diffusion space. So the diffusion-dependent process for the CO2 gets less important. It becomes more CO2 removing in the central airways. Mm-hmm. So the bulk flow or the convection. That's why we separate the two and say CO2 is more
ventilation,
convection, volume change. It's true because we have quite a strong diffusion gradient, and then it becomes, the diffusion-dependent process becomes less important or less contributing to it. So that's why the separation between CO2 and oxygen is important.
Another question, in the research, have we looked at the differences that modes of ventilation may pose on this? In particular, you know, the two major methodologies of either flow targeting or pressure targeting and what that effect might have. It seems like the technologies you spoke of would have some insight or would allow us to learn more about whether or not we're really doing anything between these different mode methodologies other than injuring the lung.
Yeah, look, that brings us back to the EIT images that we've seen where we can locate where the volume change is occurring. So the functional assessment doesn't tell you where it's happening, it is just telling you it is happening. So if you have a combination of an EIT plus an inert gas washout, first of all, you can anatomically locate where the volume change is occurring and how it impacts on the maldistribution or improving the maldistribution. And looking at the EIT data, we see very clear differences if we have a spontaneous breathing subject compared to a fully controlled ventilation. We can say that we can measure these huge differences, but we can attenuate sort of these differences by optimizing PEEP. So you see, I would see a combination of EIT, which is, again, you just put a belt on and use the gas washout and then start comparing these different modes. I have no doubts that you would see huge differences or measurable differences, but unfortunately, it's hardly been done.
Okay. Graham or Ihab, do you have?
Yeah, I just quite curious. Two things. I was thinking about spontaneously breathing patients in control, like you showed. Then I thought about a mode like APRV, which is like a high CPAP mode, but all breathing is spontaneous for the odd release and so on, which is, I suppose, in some hands is a popular mode. Do you think a mode like that, what would you expect to see from this technique? I mean, I know I'm only guessing, but when we look at a control mode like PCV or volume control, would a combination mode like APRV have a different washout? Or
I would have to speculate, Graham. I wouldn't be able to predict how it's going to look like in a way. It's we need to investigate it, and unfortunately we haven't done these so-called physiological experiments with these different modes. I think the best way probably is doing some animal work in that sense, because what you don't want is a clinical, or using humans in an ICU, because you have to, again, different pathologies. Not everyone has the same
Sure.
pathology. So the difference is that you measure or may not measure may be contributed because you have inhomogeneous population
Correct.
disease
Correct.
measures. So I think the only good approach could be in an animal experiments with or without lung injury, and approach it. I mean, you may remember we looked a little bit at with the recruitment and DIT and sulfur hexafluoride in the animal lab.
Yeah.
You can repeat in the animal lab with the smoke and inhalation injury that we use. You can start predicting what you're going to measure. But I would be cautious in a clinical environment because of just the differences from patient A, B, and C.
I could imagine companies who manufacture ventilators would be horrified from a regulatory side saying, "Oh, now we're going to have this bottle of gas, which with no control." I mean, it's a bit like nitric oxide when you start talking about a third-party topic, being used with a ventilator, and everybody says, "Well, you can do it at your own risk." Nobody is going to underwrite it.
I think there's several hurdles why we haven't used it. Is I think one hurdle is it's not easy to understand. From a marketing point of view, you need to have nice pictures, simple graphs, simple explanation, one knob to turn only, and this is high-end physiology. And if we find a way to translate that, the only way I could see it is that you have a fully integrated system within the ventilator. No one actually sees where the gas cylinder is stuck in there, and you have ventilation distribution marker 1 equals convection problems. Ventilation maldistribution marker number 2 indicates diffusion problems.
Right.
High value is bad, low value is good, and then you could take it into the clinical environment.
Yeah, I think we have precedent as well. If you look at the 7200, it had a metabolic monitor, the 7050 built in, and there were gas tanks in there, and we used mass flow controller to administer sequencing of different gases for calibration purposes. I know that there's tanks on the side of the balloon pumps, or at least they used to be, on some of the various balloon pumps and valves. And I think, as you said, a E-cylinder on an SF6 is going to give you 100 tests. You're not going to be changing it too much. Other types of gas, I assume, would be the same. I know in the things I've looked at, the things we're working on, you're getting 500 tests for E-cylinder. So it's almost as if you can connect it and walk away and then just, administer it. From my standpoint, the information that it yields is so critically important in the application of forced ventilation. I just don't understand why we haven't adopted CO2, not for comparing Untitled to, PA CO2 or anything like that. We did some agreement analysis a long time ago and found out, it may correlate, but it doesn't agree. In this case, knowing an alveolar volume or knowing a measure of VDVT and then adjusting your thinking of how you're applying the ventilator, it just seems the safer way to go. We talk about part of the reason why I asked the question of oximetry I'm sorry, about oxygen versus CO2 is I was thinking we prospectively look at oxygen today and manage oxygen changes, but we don't do the same for ventilation. We kind of make the changes and look for the curves and see how much damage we've done to say, oh, we shouldn't do that. And that's kind of that's where I'm sitting on this. I understand that people are very, very busy at the bedside, and it's imperative that anything new not impose work, talking about imposed work, not impose work, literal work on the caregivers, and that it's simple to understand. And I think that these technologies have that promise. We just need to work with the manufacturers to get it to that level of usability, if you will.
Yeah, I agree. There's the technology for the sulfur hexafluoride with the infrared signal. You can switch. Siemens built one that you can measure CO2 and sulfur hexafluoride because you can just switch the wavelengths.
Yeah.
So it's you have a CO2 sensor anyway in your airway, and then.
Yeah, it's already there. And I am cognizant of instrumental dead space, but if we know what we're doing, then we can also assess the impact of that instrumental dead space.
Yeah.
Because I do believe it's a risk, as Professor Lelouch says so often, it is a risk to offering a good mechanical ventilatory breath.
Yeah.
Ehab, do you want to
jump? I have a quick comment. Well, first of all, thank you for the talk, Andreas. Very great, and happy respiratory week for everybody.
Yeah.
I was very interested in EIT as you talked about it, and when you talked in the beginning of the talk about the ventilation difference, say for this is the head of the top part of the lung and the versus the bottom part, and you talked about when the dependent lung, the right side down. Here's my thought: when we do. I'm not sure if you talked much about the prone position. And can we homogenize a little bit of the lung? And the reason I'm asking those is because I had some experience when we put the patient prone, and most of the time they put the head of the bed tilted up. And once you put flat or the head down, like reversed, Trendelenburg position, there is a big change of tidal volume. And I'm actually collecting the data now, and I have like an average of like almost 85 milliliter per breath just by manipulating, putting the head of the patient down. And I'm not very clear on why this happens. The traditional thinking would tell you no, the more you raise the head of the bed up, actually the tidal volume might improve. And I don't know how to explain it, whether it's like pleural pressure differences or.
It's probably the function of the diaphragm or the position of the diaphragm. We know if you place someone from supine into prone, you homogenize the ventilation distribution.
Right.
And the evolution was that we humans we're obviously walking on 4 limbs. And the diaphragm that we still possess is still a diaphragm that originates from the time when we were walking on 4 limbs. So there is no surprise that prone position gives the diaphragm a better action, a better strength. And by placing someone head down, I'm not sure if I have to speculate. I can't say for sure, but having head down, the diaphragm, obviously the dome-shaped diaphragm, that the anterior portion of the diaphragm is completely stretched, and where you get the posterior or the back part insertion of the diaphragm gets actually more space to move. Because we know the anterior part of the diaphragm doesn't demonstrate a lot of movement. It's really happening in the posterior part. And that's why in prone position, all of a sudden that posterior part gets a lot of space to move. And by having someone completely head down, I think you may block the anterior part completely and give the posterior more room to move, but I'm not sure. You would have to go and measure. You put an EIT around these chests and see what's happening and where it is happening. I mean, that's an excellent idea. You put an EIT on and then start looking where is it happening, because you can measure it. Yeah.
Right. Unfortunately, I don't have this EIT technology available to me, but I try to, see like if I'm basically changing. Those people are paralyzed, just to make sure, so it's not an effort related. But I thought, like, would the esophageal pressure, like, meaning, am I changing the chest wall compliance to the?
It's very hard. It's very hard to say. There's so many factors that may influence. I wouldn't be sure, and I would say let's find out instead of trying to speculate. Yeah.
Okay.
You have to get some volunteers now.
Well, I was thinking about that today. I used to try everything I could. In fact, I'm doing a gravimetric test right now on, funny enough, an Air VO2, just to see how they heat the plates and understand how their software control works. I've instrumented everything up. And I was laughing because I looked at this transducer and I said, I wonder, I started breathing on the MIDI logger, which is a data collection system, and looking at all the temperatures and trying to decide where I was going to instrument the system. And I thought, I wonder if, since I have pressure sensors, should I try and stick this up my nose? I looked at the end of the J wire and I'm like, that looks pretty sharp. I better not. Point being, we used to do that all the time. We used to make sure that we tried any ventilator methodology on ourselves before we asked patients to do that. And I will tell you, there were a number of times I put a stop to projects because I was about to die. I felt like, I want this out. But I used to try stuff on myself before we went forth. And so I'll be a volunteer. I was going to ask you, Ihab, the head of bed, elevated even in prone, is some of that related to VAP? Are they trying to mix, head of bed elevation and semi-recumbent positioning with proning, and therefore they want, or is it your access for the nursing staff to get, this or?
Yeah, I think part of it is just everybody usually used to the head of the bed elevated. It's part of the VAP, as you said. They're worried about the tube feeding because I usually start tube feeding continuous proning, so they're worried about aspiration. And it started for me by mistake, like by chance. I was trying to put a central line, so I put the patient down, and it's like, whoa, look at the volume went. It was like, let's go more. And it's like, wow, look at the volume, and it sustained for like half an hour. But of course, the intraocular pressure and the intracranial pressure is a concern, of course. But
you increase the CVP.
You'll have to measure
Have a look at spinal patients when they come back, puffy eyes and face and whatever, petechia even sometimes, because they had to be in 9 hour and prone, head down as well.
Actually, most of the studies that I see in the literature are all coming about from ophthalmology, about the effect of Trendelenburg but nobody is looking at the lung, so I'm just raising a question.
Suggest to put an EIT on or some imaging technology and experiment, and probably first in healthy subjects, or it's quite hard.
Yeah, true.
A good question.
Well, this has been a great discussion. Thank you, Andres. Thank you for the presentation. It was wonderful. And we'll get this out quickly because I do want people to hear about this and to move forward on it. Anybody else have any parting comments or anything to say?
No. Thank you, Anderson. Very nice meeting you.
Yeah, nice to meet you too.
Thank you, Steve. Thank you, Graham.
Thanks, guys. Good to see you all.
Okay. See you next.